From Pixels to Biomechanics, for papers reconsidering what laboratory-grade motion analysis actually requires. The shared premise across these 4 papers is that learned visual priors may be sufficient to approximate laboratory-grade biomechanical measurements from monocular video. Whether this approximation holds at the precision required for individual-level clinical decisions, rather than population-level screening, is an empirical question these papers do not fully resolve. OpenCap Monocular applies constrained musculoskeletal optimization downstream of a video pose estimator. Across all 4 papers in this group, upstream pose accuracy functions as a shared ceiling, forces, muscle activity, and biomechanical attributes are all bounded by the fidelity of the initial 3-dimensional pose estimate. Improvements in video-based pose estimation are therefore likely to propagate into all 4 systems simultaneously, suggesting that the field's current investment in this problem may have compounding returns, though the magnitude of that propagation depends on whether pose errors are systematic or random. BioHuman's 10 million sample training corpus is generated entirely through musculoskeletal simulation. The simulation-to-real gap for electromyography is less well characterized than for kinematics. Simulation can reproduce joint angles with reasonable fidelity, but muscle activation is shaped by individual motor strategies that simulation does not capture. Whether the model's outputs correspond to measurable EMG in vivo, particularly during high-load athletic tasks, is not established by this paper. The approach is plausible for population-level screening, but may require individual calibration before any clinical application. Pixels to Newtons claims accuracy comparable to invasive biomechanical simulation, but the reference standard here is itself a model-based approximation of in vivo contact forces. The compound uncertainty, video pose error propagating into a simulation-based reference that is already an approximation, means the absolute accuracy of the contact force predictions remains difficult to bound independently. For injury risk stratification, the more operationally relevant question may be whether the model correctly ranks individuals by injury risk, a test that would require prospective longitudinal data not yet available. Biomodules plug-in architecture decouples biomechanical attribute prediction from the choice of pose estimator. The practical implication is that errors from any upstream estimator propagate into biomechanical outputs through a learned, non-transparent mapping. Whether this mapping generalizes to movement populations not represented in the human 3.6M alignment, specifically, high-velocity sport-specific actions, is uncharacterized. The architecture is potentially valuable, but the generalization boundary requires explicit out-of-distribution evaluation before deployment in athletic contexts. Collectively, these 4 papers suggest that video-based biomechanical analysis may reach screening-grade utility in the near term, while individual-level clinical precision will likely require additional anatomical priors or subject-specific calibration. The consistent upstream dependency on pose quality implies that a focused advance in video pose estimation could benefit the entire stack simultaneously, though whether that advance transfers to fast, occluded athletic motion remains the open empirical question.